The goal of today's lab is to investigate one of our gas laws. The gas law that we'll investigate today relates the temperature and the volume of a gas. Its name is Charles's law. The gas sample whose temperature and volume we're going to change is in this tiny little glass tube called a capillary tube. So a capillary tube is closed at one end and open at the other, and inside this tube we have a tiny plug of oil. The way I did this was I got the tube really hot on a hot plate and then stuck the end into a bowl of oil just for a brief second so that it pulled a little bit of oil up in there. So now I have this trapped gas sample. One of the major assumptions of this lab is that the diameter of this tube won't change, which means that if we measure the length of the tube and how that changes, we're actually measuring the volume of the sample of gas. So in order to measure the volume, we need to measure the length. In order to measure the length, we need a ruler. And what I'm going to do is I'm going to attach this tube to my ruler. I'm going to be very careful as I do this to line the 0 on the ruler up with the beginning of the gas sample at the bottom of the tube. So the bottom of the tube is a little bit thicker. The very bottom here is mostly glass. So I try to do this very carefully so that the 0 mark on the ruler lines up with the bottom of the gas sample. And now I'm going to read my initial volume. Actually, no, I'll put this in my ice bath first. So I'm going to put my sample of gas into the ice and a thermometer into the ice. And I'll let these equilibrate for just a minute before I take my measurement. So I've let this system sit in my ice water bath for, just a little while. Keeping the air sample under the ice water, I'm going to move it up to the front so that I can see the length of the tube. I'm going to have to get down here pretty close. Looks to me like I have I'm going to call that 6.49 centimeters. All right, let's get the temperature in the ice bath. It's not going to be exactly 0, and you'll talk in Chem 124 about the colligative properties that make this temperature not exactly 0. That being said, it's really close. I would say that is 0.01. All right, we're going to increase the temperature, and the first thing we're going to do is scoop the ice out. We'll be able to reuse some of this ice for the second trial. If we have to melt all of the ice as well as increase the temperature of the water, that's going to take a long time. We learned in our previous labs about the heat of fusion of ice. All right, that's most of the ice out of there. To increase the temperature further, we're going to need our Bunsen burner. The goal here will be to take length measurements of the tube, or of the air sample in the tube, about every 10 degrees Celsius. So we will try to watch both the thermometer and the ruler, so that as the temperature hits 10.0 degrees Celsius and 20.0 degrees Celsius and so on, up to 80 or 90 degrees Celsius, we'll write down the length of the air sample at each of those temperatures. I've used this burner earlier today, so I'm just going to turn the gas on and light it. Again, I wouldn't do that if I hadn't been using the same burner earlier in the day and if there were other people in the building using gas. I am going to turn this flame down just a little bit. I don't want to heat this sample too quickly because it's a challenge to keep track of the temperature as it changes. It's important that I keep the thermometer off the very bottom of the beaker, and important that I keep the water sort of moving around. I can get a pretty strong difference in temperature between the top and bottom of this beaker if I'm not careful. My temperature's rising up to maybe 3 degrees. to 5 degrees. In the early parts of this experiment, it's hard to see the numbers through the condensation. Later it gets hard to see as bubbles start to form and it starts to think about boiling. We're at 8. We're past 9. Almost 10. .78 at 10 degrees Celsius. We may at some point have to pause and add a little more water if our liquid level, or if our air sample rises above the top of the liquid. We're at 15 degrees. Turn the heat up a little bit, just because the temperature's not changing very quickly. We're at about 17 degrees. All right, we're almost to 20. 7.07. All right, we are almost to 30 degrees. 7.29. Past 449. 7.71. I think I misspoke last time and said that we were almost to 50. In fact, we were almost to 40 last time. Now we're almost to 50. 49 in a little bit. And this is kind of fun. Yep, at 50.0, we're at 8.00. 60 is at 8.31. All right, we're passing 69 degrees, heading to 70. And at 70 degrees, we're at 8.58. All right, we are nearly to 80 degrees. This will be our last data point. The oil plug is getting really close to the top of the tube as we go. We don't want it to come out the top. And that's going to be at 89.0.
So obviously this Charles's Law lab is a little bit different from the one that's in your lab manual, but the basic idea is the same. You'll notice I only did one trial here. Part of that was because I realized partway through the tube that I was using had been used previously, and I'm fairly sure the oil wasn't making a good seal anymore. I think a little bit of air was leaking in around that. I'll leave it to you to figure out how that might have affected the results. To do the analysis for this lab, you're going to need to create a line, a scatter plot of the data and a line of best fit, and then you'll use the equation of that line to calculate what absolute zero would be in degrees Celsius. If you have problems with that or any other questions, just send me an email.